This is a chem study film produced by the Chemical Education Material Study for use in its course in chemistry. Here is a piece of metallic sodium in a beaker. In this container, we can warm the sodium and at the same time surround it with chlorine gas. First, the sodium melts. Then, as it vaporizes, the reaction begins. In this reaction between sodium gas and chlorine gas, each sodium atom loses an electron to a chlorine atom, and the ionic substance sodium chloride is produced. In the reaction, a 3s valence electron from each sodium atom has been transferred to a chlorine atom, as shown on these orbital boards. Neon is the element just preceding sodium in the periodic table. It has only one electron less. Let's see if neon reacts with chlorine. First, the beaker is filled with neon. Then it is heated, just as we heated the sodium. Moisture condenses on the outside of the beaker at first, but it disappears as the beaker warms. Now, as chlorine gas is added, it can be seen mixing with the hot neon gas. Yet, no reaction occurs. Neon is inert, in contrast to sodium. One of the factors that determines the difference in reactivity between sodium and neon is the ionization energy. In this film, we shall see how ionization energy is measured and how it varies. To show one way in which ionization energy can be measured, let us first work with the element sodium. The ionization energy is the energy required to remove an electron from an isolated atom, and in metallic sodium, the atoms are not isolated. However, when metallic sodium is melted and vaporized, individual isolated sodium atoms are formed in the gas phase. This representation of an isolated neutral sodium atom will help to show what is meant by ionization energy. When a sodium atom absorbs energy, for example from a photon, the single valence electron may be ejected, leaving a sodium ion. This is the process that occurs when we measure ionization energy. Ionization energy, then, is the minimum energy needed to remove an electron from a gaseous atom. The energy needed to ionize the atom can be delivered to the atom in the form of light, heat, or electron bombardment. Here is an experimental device for measuring ionization energy. It consists of a vacuum pump, several reservoir bulbs of gases, and an apparatus in which the electrical conductivity of gases can be measured. Ionization produces an electron and a positive ion from a neutral atom. Thus, the electrical conductivity of any gas present will show a sharp increase when ionization occurs. The cell, which is placed in an oven, contains 2 electrodes so that the electrical conductivity of any gas between them can be measured. The wires through the cell walls connect the electrodes to a battery so that an electrical current flows when ions are formed in the gas. The meter in the circuit indicates the amount of electrical conductivity. This meter is so sensitive that it will even detect the extremely low conductivity of distilled water. As sensitive as this meter is, we are still unable to detect any conductivity in the empty cell. If a gas is placed in the cell and the meter shows that current is flowing, it is due to ionization of the gas. For this experiment, the source of energy used to ionize the gas will be light from a mercury lamp. The light is directed by a series of mirrors through a quartz prism. Then it enters the cell, where it may be absorbed by gas atoms to form ions. All the light that enters the cell must pass through this slit, which admits only a single frequency at a time. Now let's cover the lamp, turn it on, and see how the instrument works. The light passes through the prism, which separates it into different colors. Each color of light has a characteristic frequency which determines the energy. The slit admits a particular frequency to the cell. Now we have placed the cover on the instrument. The micrometer head, which controls the quartz prism, allows us to select a single frequency or color to pass out through the slit and enter the cell. Green light has a frequency of about 7 times 10 to the 14th cycles per second. As the color changes from green through yellow to red, the frequency decreases to about 5 times 10 to the 14th cycles per second, and a correspondingly lower energy. Turning the micrometer head the other way, we go from red to violet, and then, continuing to still higher frequency settings, ultraviolet light comes from the instrument, but our eyes don't respond to it. We can find the energy of any particular color of light by multiplying its frequency, nu, by the conversion factor, h, Planck's constant. Now let's proceed with the experiment. There's sodium here in the sidearm of the cell, so that when the oven surrounding it heats, sodium vapor will fill the cell. In order to make our measurements on pure gaseous sodium, we must first open this stopcock and pump all the other gases from the cell. This gauge shows the pressure in the cell. For our experiment, the pressure must be less than 1 micron, less than a millionth of an atmosphere. Now we have a good vacuum, so we'll turn on the oven and heat the cell. As soon as the sodium starts to vaporize, we will seal off the cell. The sodium melts, and when it strikes the hot glass, it boils. Light of a known energy shines through the oven and cell windows and into the gas. We'll begin with low energy red light. Watch the meter while we slowly increase the frequency of light entering the sample. There, the meter reading becomes large, indicating a large increase in the conductivity of the gas. The high-energy ultraviolet light has ionized the sodium. Let's go back and measure the lowest frequency which first causes ionization. Let's increase the frequency slowly and watch the meter more carefully this time. There, the conductivity rises rapidly. The micrometer reading corresponds to an ultraviolet frequency of 12.4 times 10 to the 14th cycles per second. Let's consider this diagram to understand what happened. The high-energy light photons ionize the sodium atoms. The electrons which are released go to the positive electrode, and the sodium ions move to the negative electrode. Electrons flow, and conductivity becomes appreciable. Now let's take a look at this process on the molecular level. A sodium atom absorbs a photon, and almost immediately an electron is ejected. The resulting charged particles then move under the influence of the electrodes. This process is called photo-ionization. A sodium gas atom plus a photon gives a sodium gas ion plus 1 electron. With this equation, we can calculate the ionization energy of sodium. We have determined that nu equals 12.4 times 10 to the 14th cycles per second in this equation. Now, multiplying by the conversion factor, H, 9.53 times 10 to the minus 14 kilocalorie second per mole, we find the ionization energy of sodium is 118 kilocalories per mole. Considering the simple apparatus which we have used, this value compares well with the accepted value of 118.4 kilocalories per mole. We have demonstrated that one of the ways to measure ionization energies is to use photons to provide the energy for ionization. Another way is through bombardment with fast-moving electrons. This alternate method permits us to check our earlier result, and it can readily give much higher energies. In this cell, we generate electrons and make them move very rapidly by strong electrical forces that can be easily controlled. A diagram will help clarify the experiment. Again, a circuit of 2 electrodes with a battery and meter will be used to detect current, hence the presence of ions. In order to obtain fast electrons as our source of energy, we first add a filament to the cell. The filament is connected to a battery. The filament heats and emits electrons from its surface. There is a metal screen through which most of the electrons can pass. It is called a grid. The grid is connected to a source of positive voltage which attracts the negative electrons. The energy of the electrons is controlled by the value of the positive accelerating voltage. Knowing the voltage allows us to calculate the energy of the electrons. As the accelerating voltage is increased, the electrons are given more and more energy. Note the similarity to the previous experiment, except that instead of photons, electrons pass through the cell. When the bombarding electrons acquire high enough energy, their collisions with gaseous sodium atoms produce ions, and the conductivity of the cell rises, as shown by the meter on the left. Now let's proceed with the experiment. Once again, all other gases must be removed from the cell. Again, we'll use the vacuum pump. The gauge shows that there is a good vacuum. When the cell reaches a temperature sufficient to vaporize the sodium, we can begin. Now we're all set. As the accelerating voltage is increased, the bombarding electrons carry more and more energy. Very little current flows through the sodium vapor, as shown by the ammeter on the left, until the voltage reaches a critical value. Then the current shows a rapid rise. Let's repeat, this time carefully reading the accelerating voltage at which a large increase in the current occurs. These random fluctuations are not meaningful. There, ions are now being produced. The voltage meter reads 5 volts. On the molecular level, an electron with sufficient energy ionizes a sodium atom, producing a second electron and a positive sodium ion. The sodium ion is attracted to the negative electrode, and the electrons are attracted to the positive electrode. The process of exciting a sodium atom so it can eject a 3s electron is represented by this equation. The energy comes from the bombarding electron, shown on the left. The ionization energy of sodium can be calculated from the measured accelerating voltage of 5 volts. An energy of 5 electron volts was given to each electron. We can change the units to kilocalories by multiplying by the factor 23.1. Thus we obtain about 115 kilocalories per mole with an uncertainty of about plus or minus 10. This is good agreement with the value determined by the photo-ionization method, 118. Now let's use this electron bombardment method to measure the ionization energies of some inert gases. In these bulbs, we have samples of 3 of the inert gases. Through this tubing, we can fill our cell with any one of these 3 gases. Let's start with helium. The cell is already empty, so we can now admit our sample. Helium is a gas at room temperature, so we don't need to heat it. It takes a voltage considerably higher than that for sodium to cause the ionization process to begin. Now watch the meter on the left. There. This sudden large rise indicates that ionization has occurred. The reading is about 25 volts, nearly 5 times the value for sodium. This value is in reasonable agreement with the value we find in a reference book, 24.6 volts. This more precise value gives an ionization energy of 567 kilocalories per mole. Now let's take the next gas, argon. The helium has been pumped out of the cell and argon added. We proceed as before. There we go. Ionization begins. The reading is about 16.5 volts when ionization occurs. The accepted value is 15.8 volts, which corresponds to 363 kilocalories per mole. Now let's try the third gas. The argon has been removed, so xenon can be added to the empty cell. Now we're ready to measure its ionization energy. The reading is about 12.5 volts this time. The accepted value is 12.1 volts, which corresponds to 280 kilocalories per mole. From the book, we've added the ionization energies of krypton and neon to our list. We see now how the ionization energies are related to the atomic numbers. The values are all high. Remember, the value for sodium was only 118. Let's plot these ionization energies against atomic number and observe the trends as related to the periodic table. Helium, with atomic number 2, has an ionization energy of 567 kcal per mole. It goes here. In a similar fashion, we can plot the rest of the inert gases in our table. We can see from this plot that the ionization energies of the inert gases decrease with increase of atomic number. The ionization energy of the alkali metals can be added to our plot. Lithium, sodium, and the others. The ionization energies of the alkali metal group are all much lower than those of the inert gases, and they decrease very slowly with increasing atomic number. With this same chart, we can show the ionization energies of many elements. Within a given row of the periodic table, the ionization energy tends to rise as the atomic number increases. This characteristic trend is repeated in each row, the same sort of repetition we find in the chemical properties that give rise to the families of elements. We shall find that the ionization energy aids us in explaining the existence of these families. Ionization energy, then, is the minimum energy needed to remove an electron from a gaseous atom. We have explored 2 measurement techniques: photo-ionization electron bombardment. We have compared the ionization energies of the inert gases to those of the alkali metals. We have indicated how, across each row of the periodic table, the ionization energies regularly increase, forming a pattern which not only helps us explain the regular trend in chemistry from element to element, but it helps us understand the very existence of the periodic table.